today we are going to start with the central limit theorem for the average random walk in random environment. Okay, so if you remember well, so far we have only proved the central limit theorem for the reaching times. And now what we want to do is to translate this result into a result for xn. Okay, I will just cite and prove the result for the average walk, but you can have a similar result for the quench walk if you want. You just have to be a bit careful about the recentering. Okay, so what's the theorem? Well, we are going to assume that this is smaller than 1, so in particular, okay, I'm adding this, but by Jensen, this is a consequence of that. Okay, so we are transient to the right. Consider xn with distribution p0, p0, I guess. And then what I'm saying is that xn minus nv over square root of n converge in distribution to z where z converge. Okay. This double arrow means convergence in distribution. Where z is a centered normal with variance sigma square over v3. So yeah, sigma square is okay. Let's start with recalling what v is. V is 1 minus e rho over 1 plus e rho. Okay, and well, you can check that by Jensen again. This assumption implies that this is positive. Okay, and sigma square. Well, it's the sum over j in z of the covariance of u1 uj, where uj is equal to tau j minus 1. Okay, I mean you can decompose sigma square into two things if you want. Let me do this. So sigma square, it's well the sum over the covariance under E of E0 omega U1 E0 omega Uj. And here I had to add the variance yeah, this is true, and I think I have to well, okay. The expectation of E0 omega U1 square minus E0 omega U1 square. Okay, so this is, I think this is what was sigma 1 square, and this was what was sigma 2 square. And I mean, basically, when you write this, you can write it as a sum, as the sum of two sums. It's just that if you write, well, the covariance here between U1 and UJ, the expectation of the covariance between U1 and UJ, you get 0 because these things are independent for the quench measure. Okay? This is the covariance of the expectation, the covariance of the expectations plus the expectation of the variances. The expectation of the covariances. Okay. So yeah, just for the theorem, we will have two steps to prove it. The first one will be, well, prove that the limit when n goes to infinity of x star n minus nv over square root of n equals z in distribution. Okay, where x star n, well, it's a max m smaller than n xn. And b, well, the limit sup when n goes to infinity of x star n minus xn over log n. We are going to prove that this is finite. Almost sure. Well, I guess what we're showing, in fact, is that the sup is finite. Okay, so A, it's okay, under the assumption of the theorem, and B, if it's this only requires that the expectation of log rho 0 is negative. Okay, so for the second result, we only need yeah, we don't require yeah, that in particular we don't even require that the walk is ballistic to the right. Okay, so an observation here is that another consequence of B is that so let me write it as a proposition. We will write it back later. So, if the expectation of rho 0 to the gamma is, let's see, yeah, smaller than 1, then lim inf of xn over n to the gamma is equal to infinity. Is this yeah? Yes. Okay. Well, basically, to show this, I mean, we proved previously that the limit of xn star divided by n to the gamma was equal to infinity. if you remember. Okay, so this guarantees that when you divide by n to the gamma here, okay, gamma in 0, 1. Okay, I mean, this was really relying on the fact that this thing here would imply that E0 to 0 to the gamma was finite. To 1 to the gamma. Okay, this thing implies this. Using then the law of large number and this subadditivity estimate, you get this, and then combining it with B, you can take it as a star away. Okay, so let's prove A, and then we will enter in some discussion and see how we prove B. Okay, so okay, so this is rather straightforward. So I mean, what we are really going to prove is that the central limit theorem we have proved for tau k implies this. Okay, so, well, what we want to estimate really, okay, I mean, we want to prove convergence in distribution towards a distribution which has no atom. Okay, so it's really equivalent to proving convergence of the accumulated distribution function. Okay, so we want to estimate the probability that this is smaller than this. Okay, and this is equivalent to tau kn larger than n with kn, which is just the integer part of square root of n t plus n. Plus nv. Yeah, plus nv. Okay. So okay. So what we want to do now is well, okay. We know how tau k behave. So basically, we want to make it to write n as a function of kn. Okay, and then you will just, I mean, the probability that tau k is larger than something, we will know that it converges. Okay, provided that what's there is on the right scale. And then the fact that k depends on n, I mean, you just have to use composition of limits. There is nothing very deep here. Okay, so let's write n is in function of kn. So, okay, I'm just going to okay, write exactly what I get. So this is what I would get if I had no integer part. And okay, the fact that I have an integer part gives me an extra term here. I mean, t now is I mean, we are going to prove that the probability of this converges for a fixed t, so t can be considered as a constant. Okay, so now what we do is, well, you replace n by this expression here. Okay, so you get kn over v minus 1 over v square root of kn over v. And then to kn over v, you're subtracting something, but this thing is of order square root of n, which is of order square root of kn. So, okay, if you just do Taylor expansion, you see that this is of a constant order. Okay, here now I have a dependence in T, but okay, so I hope I can do Taylor expansion, but anyway, it's of a smaller order than square root of k. This is the only thing that matters. Okay. So yeah, this is starting to take a good shape. I mean, you see this v to the 3 appearing, and when it's going to be squared, it's going to be v to the 3. So everything looks good so far. So now, if I write the probability that this is smaller than square root of n t plus nv, well, this is, okay, this thing, let's call it, I don't know, RT. And it's just something which is a big O of 1, okay? So this is equal to, the probability that tau k n is larger than kn over v minus 1 over v square root of kn over v t plus rt of n. Okay, now if you take the limit when n goes to infinity, well, okay, you know that this thing converges. I mean, you know that, well, this minus this converges, this minus this divided by square root of kn. This converges in distribution to a Gaussian. Okay, and well, if you just subtract this, it doesn't change anything to the fact. Okay, so this thing, okay, it's the limit here. It's equal to the probability that a Gaussian of variance sigma square, well, is larger than minus t to the v to the 3/2. Okay? This is, I mean, the square root of kn disappears because this term has been subtracted, this term has been divided, and this thing finally it's equal to the probability that is smaller than t. Okay, here I'm using, well, scaling and symmetry, okay, just to get rid of this minus sign and of this v to the 3/2. Okay. Okay, so now let's go to B, and B is going to take us a lot of time, not because it's super complicated, but just because I want to show you a bigger picture that we are going to use also to do something else, in particular to study the symmetric case of the random walk. Yeah, let's move to B, but just know that we are not. Okay, this is going to be basically to take us until the end of this class to prove B. Any question for this proof? Yes? Passage to the second line? Sorry?
I didn't quite follow the second line, yeah. How do you do the passage?
Well, okay, so what I'm doing is that okay, so yeah, T belongs to R, so I'm not so much able to do inequalities. Okay, but look, you have here, you have square root of n over kn over v. Minus 1 over v square root of n plus O of 1. Okay, so now you can expand things, and you get square root of kn over v. Okay, now this is little o of this, right? So you can do a Taylor expansion. So this is minus, and then okay, you don't really care about what you have. What's the derivative of this? Well, okay, this is big O. Okay, let's just care about the effect of this thing. Okay. You have big O of, okay, 1 over square root of kn. I'm just ignoring the v, okay, but, and here I guess you should have a 2, but this is just the derivative of the square root. And then you multiply by square root of nt. Okay, you just ignore the t also because it's a constant. So this is big O of 1. But like really, the only thing that matters is that this thing has to be little o of square root of k. So this is the reason why I didn't want to give details, because this is a... Okay, any more questions? Okay, so now let me talk about potential. Okay, so let me go back to Markov chains. Okay, so I'm not recalling what the definition of Markov chain, because what the definition I'm going to introduce is actually just going to depend on the matrix. So, so let me give you the definition of what is a reversible measure for a Markov chain. So let xn be a Markov chain on omega. Okay, omega is finite or countable with transition matrix Q. We say that a measure mu on omega is reversible. With respect to Q if for all x, y in omega square, mu x q x y is equal to mu y q y x. Okay, so this is the definition. Okay. We are not going to consider only probability measures. In fact, in this class, we are going to consider the reversible measures we are going to consider are not going to be probability measures. Well, I'm just not considering sign measures, okay? When I'm saying measure, I'm really meaning non-negative measure. Okay. So you see, you don't need to remember what the Markov chain is because the definition just depends on the matrix. Okay, so why is the notion of reversible measure important? Well, because a reversible measure is automatically invariant by multiplication on the right by q. Okay, so lemma if mu is reversible and n larger than 0, then mu q to the n is equal to mu. So, yeah, this is where, for instance, this is where having non-negative measure is useful. You don't need to worry about whether these things are well defined. Okay, so the proof is completely immediate. Well, first, okay, you just need to prove it for n equal 1 because then you can do induction. And for n equal 1, you have the following. You have that if you look at mu q of x, well, this is the sum over y in omega of mu y q y x. Okay, just definition of matrix product. Okay, now I'm using reversibility to say that this is the same as the sum over y in omega mu x qxy. Okay, and now this is equal to mu x because qx is a probability. Okay, Q is the transition matrix of a Markov chain. Okay, so this is just the distribution of xn plus 1, knowing that xn is equal to x. Okay, so this is a probability, so when you sum according to y, you get 1, and you only get mu x. Okay, so another reason why this is true is that because in spirit, okay, what this says is that, if you have a Markov chain, okay, with for which x0 is distributed according to mu, okay, then this is well somehow the amount. Okay, let's see. Yeah. The probability that that x1 is equal to y and x0 is equal to x, okay, and this is the probability that x0 is equal to y and xy is equal to x, x1 is equal to x, okay. So yeah, basically it kind of means that like the amount of probability that arrives at y coming from x is the same as the amount of probability that comes from x starting from y. So somehow the fluxes in the two directions are equal, and this is the reason why this mu is going to be stable. Okay. If mu is a probability, okay, mu qn is the distribution of xn for a Markov chain with transition matrix Q and x0 distributed according to mu. Okay, just the probability that xn is equal to x, well, it's the sum over x0, xn minus 1, probability that x0 equals 0, xn minus 1 equal xn minus 1, xn equal x. Okay, I'm just writing this thing as a disjoint union. And this is the sum, okay, and there's, I know how to write this thing. It's exactly mu x0 times q x0 x1 times q x minus 2 xn minus 1 times q xn minus 1 x. Okay, and this thing is mu qn x. Okay, this is just like the definition of the Markov chain. Okay, you start with this thing, and okay, this is not the definition, but the immediate consequence. Okay, you write the conditional probability of this knowing the rest, you get this term, and then you iterate, you get all the other terms. Okay, so we are going to use it in the case where mu is not a probability, but perhaps this intuition still is kind of relevant. You can imagine like something, a Markov chain whose initial condition is not a probability. Okay, in that case, this is not a stochastic process, but okay, this is still a process defined on a space with infinite measure, and basically, this measure mu is okay. Reversibility is a way to find invariant measures. Okay, so there are several reasons why reversible is actually something stronger than this and something more interesting. But one really key feature of reversibility is that in general, this is difficult to solve, the equation mu q is equal to mu. But this is very easy to check out. So okay, it might be that reversible measures don't exist, okay? But when they exist, they are easy to find. And in fact, if your state space, okay, is Z, or if it's a tree somehow, well, the reversible measure always exists, and I'm going to give you, well, basically the way to find it. Okay, so when I say the state space is a tree, I just mean that basically, the edges along which the transition have non-zero rates, they form a tree. Okay, so let me write things. Any question? So, okay, this is the only background I wanted to introduce. Now we are going to go back to random walk in random environment. And the first thing we are going to do is to compute the reversible measure for the random walk in random environment. So you will see in the process why the reversible measure has to be unique. Well, okay, it's unique up to multiplication by a constant under the assumption that your Markov chain is irreducible, for those who know what I mean, what this means. But basically, this means that in all interesting case, you just have one reversible measure up to multiplication by a constant. Okay, so reversible measure for the random walk. Okay, so because we are free to play with a multiplicative constant, what we are going to do is we are going to set mu0 is equal to 0. And then I will write a set of equations, which is basically the reversibility equations, that will allow me to deduce the value of mu for other sites. Okay, so what we have is that, okay, let's try to deduce mu1 from mu0. So we have mu1 times q omega 1, 0, which is mu0 times q omega 0, 1. And thus, mu1 is equal to mu0 omega 0 over 1 minus omega 1. Okay, this is 1 minus omega 1, and this is omega 0. Okay, and in general, if you take x in z, you have mu x is equal to mu x minus 1 omega j minus 1 over 1 minus omega j. And yeah, this relation here, okay, it's really a rewriting of all these conditions. So this thing being true is really equivalent to being reversible. Yes?
Is mu0 equal to 0 or anything else? Because it doesn't make sense.
No, mu0 is equal to 1. 0 is equal to 1. Because, okay, like the null measure is always reversible, but it's not the most interesting one. So, yes. Thank you. But yeah. Yeah. If you put a log, this is equal to 0. So now, yeah, because you have a multiplicative relationship, perhaps it's interesting to consider logs. So let's do this. So I want to write mu x as the exponential of something. And basically, what this relation tells me is that, this is something that I will call v. Well, when it goes from x minus 1 to x, what I have is to add the log of this. Okay, yeah, for some reason, I want to write it as the exponential of minus something. So I will define for x in z, we defined vx, which is equal to the sum from I equal 1 to x of 1 minus omega I of log 1 minus omega I over omega I minus 1. So this is for x larger than 0, and minus the sum from I equal x plus 1 to 0 of log 1 minus omega I. Yes, the same thing. I'm just writing this second line for people who don't like sums when this is smaller than this. Okay, and if you want, this is the lemma. Mu defined as mu x is equal to exponential minus Vx is reducible. Okay, and yeah, again, this V, it's defined up to now an additive constant, and V of 0 is equal to 0. Okay, so because of the minus here, yes, the 1 minus omega went up. And this is, okay, somehow this is, in a sense, comforting because you start to see something that looks like rho. So, and the log of rho, I mean, it was something that you're familiar with, so I don't know. You might feel good about it. So why is okay? Why is the lemma true? I mean, let me just provide the proof. But it's simply because mu x over mu x minus 1, well, it's equal to exponential Vx minus 1 minus Vx. And it's equal to omega x minus 1, omega omega x minus 1 over 1 minus omega x, which is what we want. Any question? Okay. You can change your mind anytime. Okay, so yeah, so a few observations. So this potential here is something relatively nice. Okay, it's not completely super nice, but so yes. If you look at the increments of V, they are not IID. Okay, well, simply because okay, these things are they are the increments of V, and yeah, basically what you have at the step x is not is dependent on what you have at the step x plus 1, just because here I and I minus 1 appear. Okay, but it's not so much of a big deal because you can correct this. So you can rewrite Vx as the sum from I equal 1 to x of log rho x, and then you just have to correct this. So you have log omega x, which is, I guess, yeah, a term that you're making appear in this sum and which shouldn't be there. And you have 1 over omega 0, which is a term which appears here and doesn't appear there. And this is the whole difference, because basically, yeah, when you make the sum, basically, this discrepancy disappears. You can just make things slide. Okay, and the good news is that this thing is bounded. So for everything relevant that we are going to prove, we can ignore this. So basically, Vx is just a sum of IID random variables. Okay, so in particular, like Vx satisfies the law of large number and the central limit theorem, and even Donsker's invariance principle. So by this, I just mean that it converges to a double-sided Brownian motion. Okay, if you rescale things by square root of n and you look at it as a process indexed by r, okay, then it will converge to, well, a double-sided Brownian motion, which is nothing more than a Brownian motion indexed by r plus, and an independent Brownian motion indexed by r minus. Okay, so this is the first observation. Second observation is that just because of this, mu is not a probability. Okay, or mu, I mean, mu can be a probability. Yeah, for some environment, okay, but if you're taking IID random environment, then almost surely it's not a probability. Well, and what I mean by it's not a probability is that it's an infinite measure. Like it's not a matter of you just renormalize it by a constant and it becomes a probability. No, it's. And the reason for this is just that, well, if you take, for instance, a case where log rho 0 is negative, what you have is that the lim inf of Vx when x goes to infinity is equal to minus infinity. Okay, so just, okay, I mean, for when this is a negative, this is just by the law of large number. When this is 0, we have done it already in the second class. I don't remember. We've done it in the second week of lectures. Okay, and yeah, you don't need more because by symmetry, you can also treat the case where this is larger or equal to 0. Okay, but yeah, now what we are going to do, especially today, okay, and then is consider the case log rho 0 negative, because this is the assumption we had on our point B that we still have to prove, if you remember. And so let me, okay, and let me draw a picture, and I'm going to consider, okay, this picture, it's not completely generic. I'm going to consider that the probability that omega 0 is smaller than 1/2, that this thing is positive. Okay, so basically this means that, yeah, the increments of log rho 0, they have negative mean, but they are positive with positive probability. Okay, and in that case, if you look at the potential, okay, perhaps I don't need that much. Well, this is just something that looks like this. So you have a drift. But yeah, like it has some kind of slope. Okay, done. Okay, and yeah, the idea that okay, somehow, even if mu is not a probability, somehow mu kind of describes, okay, what the system would like to do if it was at equilibrium. Okay, so being at equilibrium, it means being in a stage where applying a step of your transition doesn't change the distribution of the system. And basically, what this tells you is that, yeah, okay, because your equilibrium state is this one, basically, the sites with lower potentials are more favorable, so that, yeah, like this fork in the potential, okay, it sees this drifting potential and it wants to go down, but sometimes in order to go down, it has to climb a little bit, so to visit sites that are less likely. Okay, and this is going to be a bit difficult, basically, to do this. And this is eventually what's going to slow down your random walk. So we are going to see basically two things. So, I mean, first, because you have this slope, but because sometimes you have these stretches where the potential is locally going up, well, sometimes there are stretches that you're going to take a long time to climb. Okay, and the other thing is that if you look now on this direction to the left, well, yeah, okay, locally you might be going down, okay, but like if you look at sufficiently far away, you'll be going up. So because of that, it's going to be very, very difficult to go back every time. Okay, it might be locally easy to go back a few steps, but if you want to go back on a step which is more than log n, okay, then it's going to be impossible because, yeah, basically, if you take your potential in a path which is a constant multiple of log n, okay, and if you choose this constant well, then you will know that for sure the potential is higher. Okay, in a whole window of size n, say. Okay, so this is what we are going to use to prove B, and we are going to prove something more. Basically, using this thing about the traps forward. Okay, any question? Okay, so now I'm going to. Okay, I think this is. Okay, we could prove things without the potential, but I think this proposition kind of justifies the idea of introducing this mu and introducing this v. So, proposition. Okay, and the proposition has no assumption. This is true basically for every omega. So, let me put two things. So, for yeah, I think I will put three results, but only one will be. Only one needs a proof, in fact. So for any x and y distinct, and t larger than 1, the probability starting from x that tau I is smaller than t, it's smaller than t times the expectation of Vx minus Vy. Okay, so this result is only meaningful if Vy is larger than Vx, okay, because if not, this is trivial. But yeah, this gives you some information, basically. It tells you that this probability, it starts to be, okay, if Vy is much larger than Vx, this probability is small for t equal to 0, and it tells you basically that the time you need to overcome this energy barrier is really exponential in this energy barrier. Okay, so let me give you a few consequences of that, which are perhaps more useful. So for any x smaller than y, t larger than 1, p x omega ty smaller than t is smaller than t exponential minus max. Then I have x prime, y prime, y, vy prime minus vx prime. Okay, so I'm going to write the proof, but basically, yeah, the time from going from x to y, it's larger than the time from going to x prime to y prime, and for this one, I have this bound. Okay, and if x is larger than y, okay, px omega to y smaller than t. So I have the same thing, but and here I have y smaller than 1 prime smaller than x prime smaller than 1. Vy prime minus vx prime. Okay, just the same thing, but reverting the order, just for the same reason. Okay, if x is larger than y, then if you go from x to y, then you will not need to cross x prime. Okay. You will need to cross x prime and y prime. So the probability to go from x prime to y prime, okay, you have a bound on this. I mean, it's basically the symmetric version of B. Okay. So these are the results. Anybody would give a shot at proving A? This is one line. No, this is, yeah, 2 lines.
On the order of the on B, it's y prime, x prime, because it's like all the other.
Sorry?
If you have like they are next to each other, the difference of the potential areas.
Yeah, so what you want is really the highest difference of potential. So, okay, let me, yeah, but this is, I don't know what the question was, but this is a good question. Because, yeah, I have to do a picture. This is x. This is y, this is x prime, this is y prime, And what you know is that basically tau, okay, y is, well, in a sense, okay, in a vague sense, larger than exponential delta v. This is what this result tells you. Okay, and yeah, basically, this has nothing to do with the order. You can just symmetrize the picture. Like, if x is here, y is here, x prime is here, y prime is here. Okay, I mean, y doesn't have to have a lower potential than x, but basically, what drives? Okay, at least one factor that drives the time that you need to go from x to y is the largest potential barrier that you're going to encounter, meaning by how much you will have to climb. Okay, and yes, so I'm doing a very simplified picture, but how much you have to climb, I mean, you may have things like this, okay? I mean, like in the end, we have a simple random walk. It oscillates all the time, but this is how you define the, okay? Okay, is this picture perhaps clearer than the result? Okay, so yeah, how do you prove A? Okay, so where does the factor t come from? Okay, so the probability that tau y is smaller than t, it's really the probability that there exists S, or n, perhaps n, in 1 t, such that xn is equal to y. Okay, and this is smaller than the sum from n equal 1 to t, px. Okay, xn equal y. Okay, so you have n terms, t terms, sorry, so perhaps all these terms should be smaller than what the exponential thing we have. Okay, so what's the value of this term? Well, is there a simple way to rewrite this? Well, the thing is that this would be true if you start from the invariant measure. Here you're starting from x, right? So the way you can rewrite this, I mean, it's a Markov chain. So you get your initial measure, and okay, let's not write the dependence in omega. So let me write just q to the n. Okay. So is there a way to bound this? Well, we want to bound this and to get rid of the q to the power n at the same time. So we are just going to realize that delta x, it's smaller, okay, in the sense of coordinate order. Okay, but this is, it's smaller than exponential Vx times mu. Okay? So this is smaller than the sum from n equal 1 to t, exponential Vx mu q to the n. Okay? I'm multiplying positive matrices, so I can replace a matrix by something which is larger. And that's it. Because this thing is equal to, okay, and this is at 1, sorry. So this is really exponential Vx t exponential Vx mu y, which is exactly what we wanted. Okay, so the idea is quite simple. Like, if you start with distribution mu, okay, the mass you have at Vy at any time is exponential minus Vy. Okay, so the measure that you have, that you reach y after t step is really exponential Vy, and then you're just comparing mu with your starting distribution. Okay, and then let me prove B and C. I will just leave it as an exercise because it's really the same. So what we have is that, okay, to y, well, it's larger than to y prime minus to x prime. Okay, for any x prime and y prime chosen as follows. And p to y prime x prime minus to x prime smaller than t. Well, this is equal to p x prime omega to y prime smaller than t. Okay, this is just the strong Markov property. Okay, this thing under this has the same law as this, because the distribution of the chain after tau x prime it's this one. Okay, is there anything to be added? I'm just trying to be careful here that I'm not doing anything super wrong. On the event to x prime finite, okay? I think now this is true and this is smaller than that. Okay. So this was page 7, and did I do page 6? No. Yes, this is 8. Okay, this is. Okay, so now we are going to explore consequences of this proposition. So I'm going to give you 2 of them, and basically to explore the consequences of this proposition, you have to explore a bit the structure of the potential. So to kind of say, to be able to estimate these potential barriers, this delta V. Position. So the A, if the expectation of log rho 0 is negative, then there exists C positive such that for all x in 0 n, Vx minus C log n is larger than Vx plus 4 log n. Okay? This means that your potential has a negative slope, and what I'm saying is that if I'm going to the right by some constant times log n, then I have to go up by some other constant times log n. Okay, this is reasonable. The second thing is that if the expectation of rho 0 to the gamma is larger than 1, okay, is, okay. Yes, okay, perhaps this is what I want to write. Then for all n larger than n0 of omega, there exists x, y in 0 n to the gamma. Let me put something here and here. I put Vy minus Vx larger than 1 plus delta over gamma. Okay, so this second thing tells you about, well, it gives you a lower bound, but this is sharp. So, okay, it gives you a lower bound on the height of the maximal potential barrier that you are going to find up to n. So basically, this is always true, but really you can put this assumption here, because if not, this is really not an interesting result. Because if this is not true, you know that this thing will be typically of order n. So so the idea is that even if you have a drift down, okay, basically if this is true, then there are some location where you have a drift up, okay, and this generates potential barrier whose height is, well, log n times 1 over gamma, basically, where gamma is such that this occurs. So basically, you can get potential barriers of order 1 over gamma log n, where gamma is exactly the thing where this is equal to 1. And here's the assumption. Yeah, here's the assumption is the right one. Okay, so I'm going to explore the consequences of these two things, and I'll try to prove at least the point A. But let's make a short break beforehand, because. let's explore the consequences of this. And the first one, I think, is the one we wanted, which is that consequence of consequence. Okay, so of A. Well, the consequence of A is that the lim sup of x star n minus xn divided by log n is finite. And the consequence of B is that, well, if the expectation of rho 0 gamma is larger than 1, then the lim sup of x n star divided by n to the gamma is finite. Okay, and note that in fact okay, so this is A plus, okay, this is two consequences, okay, plus previous lecture. So out of this, I mean, because I mean, from this we can determine. I mean, we already had the limit for this. Okay. So okay, we had the limit. The limit was equal to infinity if this thing was strictly smaller than 1. Okay, and you can take the star away because of this in this limit. So a consequence of this is that if the expectation of rho 0 gamma is equal to 1, then the limit when n goes to infinity of log xn divided by log n is equal to gamma. Okay, gamma in 0, 1. Okay, gamma in 0, 1. Well, okay, this is true also for gamma larger than 1, but this is not very interesting. Okay, so, well, this means that, I mean, this is a kind of very precise result. It tells you, okay, if this happens, then you know that you're not ballistic, you know that the velocity is 0, but you know that the way you go to infinity is really, okay, like n to the gamma. We are not very precise on exactly what it does, but okay, what is true, in fact, is that if you renormalize xn by n to the gamma, you get a limiting law. But this is much more delicate to prove, and yeah, so just with to get this in a simple manner, like using just Borel-Cantelide arguments and this potential approach, I thought this would be quite satisfying. Okay, so yeah, let me yeah, I'm doing this. Okay. What am I doing? Yes. Okay. So let's prove consequence B first. Okay. So we will prove the consequences, and then we will prove the result. Okay, so the probability that xn star is larger okay. Yeah, we might as well prove that this is equal to 0, I think, because this is the same thing. So, okay, so we will just show that the lim sup is smaller than 1, and this would be sufficient. Okay, so we just need to show that, okay, this thing decays to 0, and it doesn't need to be decay in a summable way, because then, I mean, if you want this to, I mean, we are going to show that this decays to 0 and then use Borel-Cantelli, but we just need to apply Borel-Cantelli along a geometric sequence. So you just need to show that it decays to 0, not in an absurdly slow way. Okay, so this is equal to the probability that tau n gamma is smaller than n. Okay, so this is smaller than n times the exponential of max between 0, x, y, and n, vy minus vx. Okay, and now what do we have? N gamma, sorry. And now this is smaller than n. So now we apply here B for, if you want, for m equal n to the gamma. Okay, just replace n here by m. And you get here that this is smaller than minus 1 plus delta times log n. So this is smaller than n to the minus delta. Okay, so now I just take, say, nk, which is nk, which is 1 plus delta to the power k. Okay, so I know that by Borel-Cantelli, x star nk is smaller than nk to the gamma for all k positive. And now this tells me that x star n, well, this is smaller. Well, it's smaller than x star nk for the smallest nk, which is larger than n. And this smallest nk, it's smaller than 1 plus delta n. Yeah, so yeah, delta is equal to 1 here. Okay, and we proved our result. Okay, so this was for consequence B. Okay, basically, this result here really tells you what's the largest potential barrier, and then you use our proposition here. Okay, no, I will just. Okay, I will just delete this. So for A, what do you do? we are going to do a big union bound, so the probability that this thing is larger than C log n, it's the probability that there exists, well, it's smaller, okay, than the probability that there exists an x in 0n, such that tau x minus C log okay, so that's x minus C log n is visited there exists t in 0n such that x tau x plus t is equal to x minus C log n. Okay, if this is true, then I can find some x there such that after tau x, I visit x minus C log n. And when I mean after tau x, I mean I could put infinity there. It would also be true, but I mean I'm only interested in the time horizon n. So I'm sure here that this thing is smaller than n. So this has to occur if this occurs. Okay, now this is smaller than, okay, I'm just doing a union bound here. Okay, so it's yeah, so it's just, okay, the sum over x, x equals 0 to n. And then I have P0 omega of this. Okay, but now I can use a strong Markov property. Okay, and this is equal to the sum from x equals 0 to n of the probability starting from x that tau x plus C log n is smaller than n. Okay, now I can use A of the proposition. I have, okay, n plus 1 terms, I guess. Now I have the n here that come from the proposition, and here I have exponential v x plus C log n minus vx. I have a minus here, sorry. Minus, and now yeah, and I have this is the opposite. This is Vx. This is what you have is minus the increases in potentials. Okay, and then you get, this is smaller than n to the minus 4. Okay, just because of A here, okay, this thing we have, it's smaller than minus 4 log n. Okay, so yeah, this computation is not meant to be sharp at all. If you want to identify the best C possible, it's doable. And This is not the one you get here. Okay, but this is sufficient for what we want to do. Okay, so we have stated this proposition, we have stated consequences, we have proved the consequences admitting the proposition, so now what's left is proving the proposition. And at least this will complete the proof of the central limit theorem, because we still need to complete the proof of this, which was point B of our proof. Okay, so let's go. Yeah, so all these two estimates, basically, they are large deviation estimates. And this one is the easier one because it's an upper bound, and this one is a lower bound. Okay, and this one is also harder because it's sharp, and this one is, you don't really care about the constant here. So. Okay, so let's prove things. And to prove things, I'm going to prove things for, we are going to replace V by V bar, where V bar of X is the sum, okay, the algebraic sum from I equal 1 to X, so of log rho I. Okay, just because I want to have IID terms. Yeah, the difference between V and V bar is just at most a constant, so it won't change anything in the statement. Here we have a delta. Which can absorb this constant, and here we have a C. Also, we can place this rule. Okay. So, yes. How do we prove A? So, the first observation is to transform a little bit this thing. If E of log rho 0 is negative, then there exists gamma positive such that the expectation of gamma 0 such that this is smaller than 1. Okay, I mean, this is just because this thing here, it's the derivative of this function at gamma is equal to 0. Okay, and at gamma equal to 0, this thing is equal to 1. Okay, so we are going to use this gamma. Okay, so implicitly I'm saying, let's take such a gamma and fix it for the rest of the proof. Okay, so now, we are trying to bound the probability that there exists X in 0n such that Vx minus C log n is smaller than Vx plus 4 log n. Okay, and again, I guess this is for n sufficiently large. Okay, this can be true for all n, perhaps, if you take C large. But so we just want to show that this is small and that this is summable in n. Okay, so. Well, this thing it is smaller, okay, just by union bound, of the probability that the C log n is larger than minus 4 log n. Okay, here I'm just using a union bound, so I get n terms. All the terms are equal, so I can just take x to be equal to C log n. Okay, and this gives me this. Okay. So, yes, now I'm taking the exponential. Okay, I will take perhaps. Okay, I will call this thing k, and I will write the remainder of the proof with a k. So, we want to prove that, we want to have an estimate on the probability that Vk is larger than minus 4 over C. Okay. Now, this is equal to the probability. So I'm just taking the exponential here. I'm taking exponential to the gamma. So this is equal to the probability that this thing to the gamma is larger than exponential minus 4 gamma over C. Okay. Okay? I mean, saying that something is larger than something, it's the same as saying that the exponential gamma of this thing is larger than the exponential gamma of the other thing. Okay, and now I'm good. This is smaller than, I'm just using Markov inequality. So here I have the expectation of rho 1, rho k to the gamma. And I have to, well, to divide by this, so which is the same as multiplying by the inverse, so 4 gamma over C. Okay, and this is equal to E rho 0 gamma to the k exponential 4 gamma over C to the k. And now C is the parameter we can play with. Okay, gamma is fixed, and we want to say that things hold for C large. So we can say, okay, this is smaller than E rho 0 to the gamma k over 2. Okay? This decays exponentially in k. Well, this decays exponentially, but the rate can be made arbitrarily small. So we can say, okay. This increases exponentially, but with a rate that can be made arbitrarily small. So this can be absorbed into that if we replace k by k over 2. Okay, this is C large. Okay, so what we get here, okay, is that this is smaller than exponential, okay, E log rho 0. And then you get to the E, so rho 0 to the gamma log n times c divided by 2. Okay, and well, this is smaller than n to the minus 2, okay, just by taking c large. Okay, I mean, this inequality gives you a condition on C. This inequality here gives you another condition on C. You take the max of the two conditions. Okay, you're good. Okay. Yeah, I think okay. Do you have question on the proof? I mean, the idea is that basically, you know that if you have IID random variable, the probability of them deviating from the mean is going to be exponentially small. And the way you prove this, okay, is just by taking the exponential in there and then optimize in the parameter. Okay, and if you optimize, I mean, okay, here we have done a rough optimization, but if you really optimize, you get the optimal decay here. Okay, and yeah, here, because we can play on parameters, even not optimizing, we get what we want in the end. Okay, so yeah, let me try to prove B now. And the idea of B is kind of doing the opposite. So now you want to have a lower bound for the probability of something unlikely to happen. Okay? So basically what you want to do here is to show that, well, when you go from here to, okay, when you use Markov here, you don't lose too much, provided that you have chosen your gamma in the right way. Okay, and it turns out that the gamma, choosing the gamma in the right way is exactly choosing that this thing to be equal to 1. Proof of A. Yes. No, this is B. Proof of B. Okay, so I'm going to change the statement. I think I'm going to assume that E rho 0 to the gamma is equal to 1. Okay. And I will replace 1 plus delta by 1 minus delta. Okay? And the statement, okay, and perhaps I will replace there exists by for all. Okay? So what I want to say is that if this is equal to 1, then this is larger than 1 over gamma log n minus something small. Okay, and this is equivalent because if this is true, then this thing is true for, this is equal to 1 for a smaller gamma. So dividing by something smaller here gives me the 1 plus delta I will need. Okay, so these things are really equivalent. Okay? Okay, and prove. Okay. Vy minus Vx larger than 1 minus delta over gamma log n. X. Okay, and again, this is for all n sufficiently large. And yeah, somehow, okay, I don't want to do this. I want to do this. C log n, C n log n. So again, adding a log n here doesn't change anything in the statement, just because, okay, adding a log n, it's the same as putting a 1 plus epsilon here. Putting a 1 plus epsilon here, it would be putting a 1 plus epsilon there. Okay, and that would be good. Okay, and one last comment. So we need to prove that this thing happens for all n, for all large n. So what we are going to prove is that the probability of this happening, or the probability of this not happening, decays sufficiently fast. Okay, and yeah, I don't know if this is really a concern, but sufficiently fast here does not need to be smaller than 1 over n, because again, yeah, you just need to show that this occurs. You just need to apply Borel-Cantelli along a geometric sequence. Okay. Okay, so let's go. So what are we going to do? Well, I'm going to fix a k, okay? K it's going to be of order log n, but I'm not going to tell you who it is until the end. Yeah, so this the idea of adding a log n here is really, I want to say that this max here, it's always larger than the max from I in 1n v I k minus v I minus 1. Okay. Okay, and let's put bars everywhere. Okay, so what's the big advantage here? Now I'm taking the max over some IID sequence. Okay, here when you take the max over all x and y, you have overlapping intervals. So this difference here, they are not. Here I'm just taking increments of size k, and I'm considering none. Okay, so. Okay, and here I mean I had the max. I mean I had n square variable. Now I have only n to control. And okay. Okay, I'm losing something here. So now, what's the probability that max over I in 1n v I k minus v I minus 1 k the probability that this is larger than 1 minus delta over gamma log n. Well, this is the probability okay, this is the probability that that for all x okay, sorry, it's smaller. I put some I want to show that this max is small. Okay, I want to show that this probability is small. Okay, so this is the probability that for all x, this thing is smaller than 1 minus delta. And now by independence, this is equal to the probability that v Vk is smaller than 1 minus delta over gamma log n to the n. Okay, so what I really need to show, okay, I want to show that this goes to 0. So I need to show, okay, so this is equal to the probability that, this is equal to 1 minus the probability that Vk is smaller than, is larger than 1 minus, okay. Yeah, perhaps I want this. It's not a big deal, but it's 1 minus delta over gamma log n. So yes, I just want to show that this is much larger than 1 over n, and I'll be done. Okay, if this is much larger than 1 over n, and actually this is going to be larger than this is going to be of order 1 minus something, n to the minus 1 plus something. Okay, so basically this will tell you that this thing yeah, this will tell you that this thing decreases like exponential minus n to some power. Okay, so which is great. Okay, so we want to have a bound on this. Okay, so now the probability that Vk is larger than 1 minus delta over gamma log n. Okay, it's a probability that rho 1 rho k to the gamma is larger than n to the power of 1 minus delta. Okay, and okay, now I want to do a few things. So I'm going to, okay, what I want here is a lower bound on this. Okay, I want a lower bound on this. So I'm going to write this as an indicator, but okay, perhaps okay. Okay, I want to write this as an indicator. Here I want to put rho 1 rho k to the gamma for some reason. And here I want to make sure that rho 1 rho k to the gamma is larger than n to the 1 minus delta. But I don't want to be too big either. Okay, so because I've multiplied here by something, okay, so here the fact that I'm restricting the interval is going in the right direction. Here I'm multiplying by something, but I know that this something is smaller than this. So I can just divide here by, well, an upper bound for this. And now, okay, just, okay, no, I'm just going to put it here. Okay, so now I have something there. Okay, this thing is, well, it starts to look like something that we would like. Okay, and now what we get is really, well, this thing here, it has expectation 1. So it's a probability density. So we get E, okay, so it's EK if you want, but the dependence in K is not really important. PK, sorry. So you get N to the delta over 2 minus 1. And you get, okay, and here, okay, let me rewrite this as, well, VK. Okay, this belongs to, this probably was a mistake to write it in this form. This belongs to 1 minus delta over gamma log n, 1 minus delta over 2 over gamma log n. Okay, so this is much larger than n to the minus 1. So what we want to make sure is that here, that this event here has a good probability. Okay? So, well, what's important here is that, okay, under P, okay, you have rho 1, rho k, they are IID. Okay, I mean, like if you look at the probability that rho 1 belongs to A, okay, it's just the expectation of rho 1 in A, rho 1 gamma. Okay, and things factorize. So things are IID with this distribution. Okay, so in particular, okay, and gamma is fixed. I mean, there is a, so in particular, Vk satisfies the law of large number. Okay? So we just have to choose K in such a way that, well, this will have a large probability because of law of large numbers. The good thing is that here, the lower bound and the upper bound, they differ by a constant factor. Okay, so the only thing we have to check is that the expectation of V1 is positive. Okay, because, well, these things are positive. Okay, okay, so, yeah, no, the expectation of V1, well, it's equal to E log rho 1. Okay, and I have a bar, perhaps. Log rho 1 to the gamma. Okay, and this is the derivative of E rho 1 to the gamma. Okay, and okay, so yes, I have two gammas. Okay, I have gamma as a variable and gamma as a fixed value. Perhaps we can put it gamma star. This is gamma star. Okay, and yeah, this is convex in gamma. This is equal to 1 at 0. This gamma star here is the one such that you reach level 1 again. So because of that, by convexity here, this has to be positive. Okay, so then you just take k being equal to, okay, log n times 1 minus 3 delta over 4. Yes. Divided by gamma divided by E of log rho 1 to the gamma. Okay, and you get that this thing tends to 1. So in particular, for n sufficiently large, this is larger than n to the delta over 2 minus 1. Divided by 2. Okay, so this is larger than this. Then you put it back there. So you get 1 minus something, but, okay, so now you have the inequality in this direction. And because this thing is much larger than 1 over n, when you put it to the power n, you get something really small. Yes, so okay, somehow this is a large deviation computation. From people that have already seen large deviation computation, this is really somehow the proof of the lower bound of what's the name of the theorem? Cramer's theorem. Yes, thank you. But there is something which is okay. If you want to use Cramer's theorem to prove this, it's a bit annoying because you have to choose the k beforehand somehow if you want to. So here somehow you play something similar, but you use this thing here that you don't have to divide by the expectation because the expectation is equal to 1. Because if not, you would have a prefactor that depends on k. And it turns out that if you try to optimize over every gamma, you will see that the gamma for which this thing is equal to 1 is really the right one. Well, I mean, somehow the fact that you have matching upper and lower bound for the behavior of xn in terms of power kind of tells you that this is sharp. Okay, so at least for when gamma is smaller than 1, but there is no reason that gamma larger than 1 should be different. So yeah, basically this result tells you what's the largest potential barrier is, but in the proof you get something subtler. You know actually how it's formed. You know that okay, up to some small correction, this is going to be the length, okay, of and this thing is going to be the slope. Okay, so the way these potential barriers are generated is really, during a few steps, the potential goes out of its way and it kind of mimics this. The increments are still IID, but with a different measure. This has a cost, so it cannot go forever. You do this for this number of steps, and this is what the potential barriers look like. Okay. And this ends up what I wanted to say today. I'm over time, so we'll have a shorter class tomorrow, maybe. I don't know. So tomorrow we'll start to see the symmetric case. Okay, so the symmetric case meaning the case where the expectation of log rho is equal to 0.